All right, for everyone online, we're about to start. I think the video is working for we're closed. I think the video is working for now. If it shuts off, it's bound to happen. That doesn't work. It's not worth using. The microphone's in here. That's for you.
All right, good afternoon. I think we're going to get started here. Clap if you can hear me. Clap twice. We're going to get started. It's my pleasure to introduce Rachel Ivey. She is the Director of Higher Education Programs and Grants at the Association of Physics Teachers. And we're very much looking forward to your talk today.
Thank you. So it's my job to try to keep you awake. So if you're a coffee drinker, everybody got their coffee? Okay. So like Sukanya said, I do work at the American Association of Physics Teachers. But before that, for a long time, let me use this because I'm not used to a Mac. I worked at the American Institute of Physics.
Keep going, you're fine.
Okay. And,
I had to do something really quickly.
okay. See, I can't talk without a slide.
Is that better? Should be good.
Okay. Okay, so I worked at the American Institute of Physics. They have a statistical research center there. That was its name. I think really it should have been called a survey research center because that was the primary thing that we did was we did surveys about the education and employment of physicists and astronomers. And I worked there for more than 25 years. I should tell you, though, that I am, by training, a sociologist. And I got the job because I knew about survey research methods and statistics. When I was in graduate school, it was very common in sociology to train graduate students in quantitative research methods. So that was my training. I'm not the kind of sociologist that Gabby talked about last night, who I was not embedded in LIGO, which is a shame as far as I'm concerned. But I did a lot of surveys and I collected a lot of data on two areas: the representation of different types of people in physics and astronomy, so demographics of people, and then also on barriers to people's participation. Are there differences in who gets to participate in physics and astronomy and why? Today, I'm going to tell you about two of the studies that I did about the barriers to participation. Trying to think if that's all I need to tell you so far about my background. One thing I want to say about working as a sociologist, I've noticed that in different disciplines, people use different types of statistical methods, which almost always boil down to the same thing. Like within social science, for example, psychologists love analysis of variance, or used to, and sociologists do regression often with dummy variables, which kind of comes out to the same thing. So that's just a little bit about my approach is probably different than some of the approaches that you have been taking, although I've listened and learned a lot in hearing your talks today and a little bit yesterday. So the reason why I look at the barriers to participation is kind of a circular thing. You can see here that the percentage of women earning physics degrees is much lower than, well, this is the number. This is the number of women earning physics degrees and the number of men earning physics degrees in the US. And I'm going to talk in a minute about a global study. And there is a gender gap in physics in almost every country. So it's not just in our country, but across the world, women earn fewer physics degrees than men do. And when I first started doing this work, actually I was, my expertise was in the sociology of gender, when I was in grad school. And one of the things I looked at was, well, I'll tell you a funny story about that. Well, it's kind of sad funny. I was the only woman at my level doing this kind of work at AIP. And they handed me a folder, which it was so long ago that it had transparencies in it, okay? And they said to me, here is our data on women. And I thought, I wonder why you're handing this to me, because they didn't really know about me and the sociology of gender. I'm just thinking, oh, I'm the woman, so I get the folder on women. But I decided, that inequality is one of my interests, and so I was going to go with it. And I started looking at the representation of women in physics. And at that time, people in the community tended to think that if we could just increase the number of women in physics, everything would be better. So it was just a question of getting more, and then everything would be evened out. But what sociologists know is that it doesn't matter the size of the group, because you could have two groups of equal size, and one of them could still be disadvantaged or experience inequality. A really good example of that is South Africa under apartheid, where actually it was a tiny group who disadvantaged everyone else in the country. So you have to look at barriers to participation, or what I like to call inequality, as part of understanding why these numbers are so low. When people look around and they say, oh, here's a field with no women in it, then they start to wonder why, and they figure out maybe that there's barriers to their participation, and so they're less likely to go into it. And so when they're less likely to go into it, then it doesn't attract as many people. So I'm going to talk to you about some surveys I've done, and since this is a statistical conference, I will show you some of the models and the types of statistics that we did, although not so many formulas. Let me just leave that there for now. About more than 20 years ago, I started working with the International Union of Pure and Applied Physics on global surveys of physicists to try to assess the situation of women in physics across the world. The IUPAP has several working groups. There is a working group on women in physics. It's called Working Group 5. And this working group has team leaders in every country, in every IUPAP country. You can be officially, as a country, associated with the International Union of Pure and Applied Physics. And for the different constituents in different countries, they started having conferences, international conferences of women in physics. By the way, it's really interesting how they got the Working Group 5, because it was in the late 90s, people actually said, we don't need this group, okay? And it was actually a man who argued successfully that we needed Working Group 5. But anyway, they started with the International Conferences of Women in Physics, and they wanted to do surveys because physicists love quantitative data. And we did 2 surveys with them, one at the first international conference in Paris and the second in Rio. The third conference was actually in 2008, but we decided to expand the survey a little bit, because the first 2 surveys, the respondents were instructed to forward the questionnaire to their women colleagues. So the target group was only women, but I started telling them, we can't say anything about inequality or how the situation of women is compared to men unless there's men in the questionnaire. So by 2008, that conference, we decided to expand the survey to include men, and we also expanded it to include 8 languages, including English. And I'll talk a little bit more about that in a minute. By 2018, we decided that we were going to put in a proposal to the International Science Council, which is right there, to fund a global study of the gender gap in science, not just in physics. And the 3 leads on it were the International Mathematical Union, the International Union of Pure and Applied Chemistry, and then IUPAP, which is Pure and Applied Physics. We had other partners join us because we wanted to include as many disciplines as possible. There's the astronomers, biological sciences, computing, industrial and applied mathematics, This is the history and philosophy of science and technology. Who knew there was a whole union for that? And these are just 3 NGOs that participated in the project. So this is actually the official title, and this study was started, we applied for the funding in 2016, so almost 10 years ago. And so the premise of the study was that we need to identify the various barriers that deter women from pursuing careers in scientific disciplines. There were 3 parts to the project. One was a study of gender gap in publications that was done with mathematical modeling by some mathematicians, and the database of good practices, which was assembled by some researchers on the project. And this website has all those information in case you're interested in publication differences. But I worked on the survey, so I'm going to talk about that. Oops, went the wrong way. Still going the wrong way. I will use the flipper and the remote as instructed. So I was trained as a sociologist in hypothesis-based research, meaning that before I could collect data, I needed to have a research question or a hypothesis and then only collect data that would be needed to test that hypothesis. So if you're ever like working with a committee and they're putting together a survey and somebody says, wouldn't it be interesting to put this on the questionnaire? Most of the time it's not interesting because it's not answering your research question. So I'm just telling you that so you'll kind of understand the perspective that I'm coming from. So in this first box here, we have actually what were our dependent variables. And you can see them all listed out here. I'm going to focus in today's talk on these last 2, access to resources needed to conduct science and opportunities to contribute to the scientific enterprise. These are our independent variables. It was a gender study, so of course we include gender, but we also include other variables, controlling variables, such as age, employment sector. Not everybody in the study was an academic. There were people working in other sectors. Level of development of the country that the respondent worked in, as defined by one of the UN indexes, the United Nations, and geographic region. So some of the reasons that we controlled for these, for example, include like age. If we're measuring opportunities, for example, then the longer you've been working in science, the more likely you are to have had opportunities. So if we're going to see a real gender difference, we have to control for some of these other things that may have an effect on our dependent variable. So the questionnaire, I wanted to talk a little bit how it was developed. We started with the original global surveys of physics, but we wanted to make sure that it worked in the other scientific disciplines and that it worked in other regions of the world. We didn't want it to be a survey made up by North American or European women. So we did 3 regional conferences where people reviewed our draft questionnaire and tried to help us determine if it would work in their area of the world and in their discipline. And so this is a picture from the regional meeting in Cape Town, South Africa. And these women here, except for the white woman, are all leaders in their fields in Africa. Marie-Françoise there is a French mathematician, and she was actually the PI of the project. We also had questionnaire development in meetings in Latin America and in Taipei for the Asian region of the world. I mean, one reason why you want to do this is you got to make sure that you're measuring the correct things correctly as best you can in order to determine if there's really a gender gap. The survey was launched on May 1st and closed on December 2018. We did leave it open for a long time. It took us a while actually to get respondents in China, but we did it. It was available in 7 languages. We had 32,000 respondents from more than 150 countries. It was a snowball sample, which in case you don't know what that means there's no list of physicists in the world or scientists. Gosh, I got to be careful. There's no list from which to draw a random sample. So the only way you can get people to respond in this situation is to ask them to forward their the survey to their contacts. So that's what we did, and that's called Snowball. What that means is that the results that I'm going to show you are not representative of scientists in the world. They do show differences for the people who answered the question. And because the differences, the questionnaire, because the differences are similar to other research, I think there is some, it is worth knowing. We've got 32,000 people, and it is worth knowing that the gender gap, spoiler, persists in all countries and across all disciplines. But that's my caveat for that. Here's the first page of the survey. It was available in English, French, Japanese, and Chinese, which I think I might have said in backwards order, but I'm not sure. And my apologies, because I can't tell the difference. Russian and Spanish, and then Arabic, which is actually the language that we had the hardest time getting people to respond in. We also didn't want there to be a bias toward English speakers. So we had started translating it into different languages and we had it professionally translated and then reviewed by the scientists to make sure that it was all cool as far as science goes. So here's the number of respondents by discipline. Physics had the largest number of respondents, probably because we had done global surveys of physicists before. The way that IUPAP worked is they had the team leaders in each country distribute the survey to their colleagues. And so they had already done that in the past and they were used to it. So we got a good number of physicists responding. You notice that the overall percentage of respondents was 50% women. That doesn't mean that 50% of the scientists in the world are women. It just means that that's how this one came out. And that's largely because it's a gender project, and a lot of the people distributing the questionnaire were women distributing it to their colleagues who may be more likely to be women. But physics certainly is not 37% of women in the world. Here's the number of respondents by country. You can see it kind of correlates with where science or a lot of science is done. So here's some of the details about the analysis that we did. You can see here again, here's our independent variables. Oops, didn't mean to do that. Here's our independent variables. I already talked about how age can affect opportunities to do science, resources to do science, but so does employment sector. People in academics may have different access to opportunities than people who work in industry, for example. The level of human development in a country, of course, affects your opportunities and resources because a highly developed country is going to have more of those things for its scientists. We hope. I just was getting political in my head there. Going to have more of those things for its scientists than a less developed country. Of course, we want to make sure that we control for discipline because things could be different in different disciplines. And then geographic region where different areas of the world may have different access to resources and opportunities. So the reason why we're doing all this is we want to see that if there is an effect of gender, that it can't be explained by something else. Because, well, we did a lot of different types of multivariate regressions, not Bayesian. I know this is Bayes Day, but we did, it was a very simple analysis, according to me. The kind of regression we did depended on the type of dependent variable. So we had some variables that were 0 and 1, meaning logistic regression. We did ordinary least squares. We had a categorical dependent variable. And we set our significance level very high because we were doing so many tests that we did a Bonferroni correction to make sure we weren't getting too many false positives. Okay, here's some of the models that we tested. This is only partial model that we tested. We did do a path analysis, and we started with the effect of the independent variables on opportunities and resources. I just want to go ahead and tell you before I forget that actually for physics in this survey, there were no effects of gender on opportunities. So I'm only going to talk about the effects of gender on resources. But let me go to the next slide. I wanted to let you know that because I give this talk to a lot of physicists who don't necessarily know about statistics, I tend to present things like in a bivariate manner. But that doesn't mean that I'm just showing you the results of a bivariate analysis. Everything I'm showing you is significant in the multivariate analysis. Okay, so here's our dependent variables, or sorry, here's our list of the resources that we asked people about, because you might have been thinking, gosh, what does she mean resources? Well, we asked them, do you have enough funding, office space, lab space, equipment, blah, blah, blah. There are 12 of them. We looked at this dependent variable two ways, these dependent variables two ways. First one that we did was we added them up. So there was a sum, and the dependent variable was the sum of resources. And the result of that showed that men on average report half a resource more than women, controlling for all the stuff in our model. Now that seems small, and I'm going to talk about the accumulation of disadvantage toward the end of the talk. But when you start out behind, it's easy to stay behind. You can't catch up when somebody starts out ahead of you. Like I said, it's even after controlling for our other independent variables. Another significant finding is that the higher the Human Development Index, the more resources that people had. So that hypothesis was confirmed. In the slide I'm going to show you next, this is, I'll talk about that in just a minute. This is the analysis where each resource was its own dependent variable. So the model was tested separately on each resource. And these are derived from the odds ratios that show that, for example, women were less likely than men to report having enough funding, clerical support, technical support, employees or students, and support as a working parent. These down here that say no, sorry, didn't mean to do that. These down here that say no, this just means that statistically controlling for the other variables, there is no difference between women and men. There were no resources that men reported having less than women. So there was either no statistical difference or women had less than men. And this is a finding that we've found in every global survey. We did do path models, and I didn't bring them all. In the interest of time, I wanted to talk only about, we tested for direct on career progress and indirect effects in our path model. I didn't bring the relationship between opportunities and career progress, but it does show that the more opportunities and resources that you have, the faster your career progresses. So that makes sense, right? It's not that interesting. The more stuff I have, the faster my career progresses. I did want to talk about this interaction term in case you're not familiar with the way that this type of model or a sociologist would do an interaction. These were all dummy variables, 1, 0 variables. And so the sex, I don't remember which was which, or gender, 1 and 0, male and female, and then do you have children or not children? So the only people who have a variable of 1 in this interaction term, you multiply them together, are women with children. So I wanted to show the results of this interaction where we put this in the model on career progress, because this is a finding that we've had in every global survey since we started in 2002. So this is the question that we asked them, and this is I should stay closer to the podium. This over here, bar, is the interaction term that we tested, women with children. So what this shows is that women with children, controlling for all the other things in our model, were more likely to say that they had progressed slowly in their career compared to the other 3 groups. Okay, this doesn't make a comparison among these 3 groups, but this one to the other 3. So this is a finding that we've had consistently in the global surveys, where women with children do report that their career progresses more slowly than their colleagues. Probably the primary reason for this is that most countries, most societies still assign childcare primarily to women. The responsibility for childcare is still assigned primarily to women. We collected some qualitative data on this in our surveys. And I remember one answer, a woman from Spain said, my husband took the kids to the doctor twice and he thinks he contributed to childcare. So, you know, I guess we can all work that out in our individual situations, but that was a typical answer. Okay, so I want to move on to another survey that's a little bit more recent. We occasionally do faculty member surveys. These data were collected during COVID in the spring of 2021. Most of them were conducted by, you can't see her name, I put it at the bottom, by my colleague Courtney Walsh at AIP. And I want to talk to you about how we did the sample. We did a random sample because AIP maintains a list. Like with the global survey, there is no list of scientists, but there is a list of physics and astronomy departments that's maintained by AIP. We took a random sample of those departments, and then for each sample department, we found what we believe to be all of their faculty members by doing web searches, phone calls, things like that. So it was, the sample was stratified by the highest physics or astronomy degree offered, so that we had an equal chance of being drawn if you were a bachelor's department compared to a PhD department. It included all historically Black colleges and universities because there's more Black professors working at the HBCUs than there are, at least percentage-wise. And we wanted to make sure we got as many Black faculty members as we could. There were 315 departments in the sample, and the questionnaire went out to 5,500 faculty members. It included people who were tenured, not yet tenured, adjuncts, everything, every kind of faculty member. The analysis I'm going to talk to you about, the dependent variable, is time to tenure. How long did it take folks to get tenure? Is there, and my question, remember I'm supposed to have a hypothesis. My question, or my research question, is, are there differences by demographic, by type of person, in who gets tenure more quickly? So this analysis is limited to people who had tenure at the time of the survey, and there were about 450 faculty members in it. Because of the way this was drawn mathematically, it is representative with our measurement error and non-response coverage and all that. But it is representative of faculty members in the US. Okay, so we just did ordinarily least squares because our dependent variable was years. The models included all of these independent variables: gender, rank, citizenship, race, highest degree offered by the department, public-private, type of department. That means, was it a physics department, an astronomy department, or a combined department? The highest degree the faculty member had, the years since they got their degree, everything we could think of that might affect time to tenure. And the dependent variable was time to tenure. We had some faculty members who took more than 10 years to become an assistant professor. And we figured, we didn't know from the data, but we figured these were people who probably did something else before they went into academics. The median time, so we took them out of the analysis. The median time to tenure for those left in was 9.3 years. So you do a postdoc and then get your tenure. Half the respondents, the middle 50%, received tenure between 7 years and 12 years. But when we broke it down, there were no gender differences, by the way. When we broke it down, and this is just a bivariate representation, not controlling for any of the independent variables. This is the median is in yellow, the median line, and the dark purple boxes are the middle 50%. The light purple boxes are 90th and 10th percentile, and then you can see the range in the lines there. And what we found actually in the multivariate models, you can actually see in these bivariate representations, is that Black faculty members, and also, interesting, Asian faculty members, took longer to get tenure than white faculty members. There was no difference for Hispanic, which we were kind of surprised by that. I'll talk some more about that in a minute. Here's a list of all of our independent variables and whether or not they had an effect on time to tenure. So all these institutional variables, looks like I accidentally cut off some of the words, but it's institutional variables, didn't have an effect on time to tenure. Whether or not you took a postdoc did have an effect on your time to tenure, because of course, if you took a postdoc, which almost everybody does, that lengthens your time to tenure. If you stop the tenure clock, that lengthens your time to tenure. The demographic variables down at the bottom, like I've already mentioned, we found that Black and Asian American faculty members took longer than white faculty members to get tenure. You can see here, I got to stand next to the microphone. You can see here that, sorry, white was our reference category. So when we did the regression with dummy variables, everyone is compared to white faculty members. So the comparison that in our model is just between Asian and white, Black and white, Hispanic and white. So to sum up, in the multivariate models, Black and African American faculty members on average received tenure 1.5 years later, and Asian American faculty members almost a whole year later than similar white colleagues. So what are some conclusions from these two studies? Because it's not, I'm always interested in, as a sociologist, not in just the data, but what can we do with it? From the gender gap study, we learned that women receive fewer resources to conduct research. Having children has a larger and negative effect on women's careers compared to men's. From the faculty member study, we learned that Black and Asian faculty members receive tenure later than white faculty members. The mechanisms through which this tenure process occurs are largely unknown. The article was just published, well, it seems like just to me, it was published in 2023 in Physics Today. So I didn't put the reference up, but you can go find it there. One thing that happens is, well, I'm actually going to talk about a process by which it happens. I wanted to say a note, though, about the Hispanic faculty members. It was surprising to us to find no statistical difference because there is a lot of qualitative research that documents barriers for Hispanic faculty members. So for it not to show up in a quantitative study was surprising to us, but that's why quantitative studies can be limiting, at least in the social scientists. You need both kinds of social sciences, you need both kinds of data to figure out what's going on. So I next want to talk to you about a sociological theory that can be applied to these types of data. And this is a really famous sociologist. There's lots of funny stories about him that, I don't know, I don't have time to share, but he was, I believe, still alive when I was in graduate school. This was published in Science in 1968, the journal Science. And the guy's name was Merton, and he called it the Matthew effect. And what it means is that in science, if you have resources, you're more likely to get more resources and your career goes further faster. He called it the Matthew effect, not because of some guy, but because of a scripture passage, actually from the Bible. Who knew, right? This is the scripture. For to who everyone who has, more will be given, and he will grow rich. But if you don't have anything, even that will be taken away. And I'm like, okay, religion. I'll let my brother, who's a minister, try to explain that to us, but he's not here, so we'll move on. This is a graph of it. Women and people from other minoritized groups. What do I mean here? Black faculty members, Hispanic students, indigenous. These people experience cumulative disadvantage. So because how does it work? Let's take Black faculty members, for example. If you're in a department that's unwelcoming and you're a Black faculty member and they're unwelcoming to you, you may be less likely to ask to be participating in collaborations. Because you're not in these collaborations, you're going to be less likely to get the publications and then less likely to get the funding. And because you didn't get those things, you can't get the next grant. And pretty soon you're on this red line down here while the white colleagues are up here because you were excluded from some of the resources like collaborations that were available to your white colleagues. Sociologists, by the way, kind of talk bluntly about race, so y'all excuse me while I do that. This is another picture of the cumulative advantage. A lot of times it's not called the Matthew effect anymore, but just cumulative advantage or cumulative disadvantage. I like this chart because it kind of shows like some of the things that affect faculty members. More publications, more access to collaboration, less admin and teaching. And then you start getting the awards, the funding awards, the publications. And when you start getting those, you get more and more and more because we know his work, right? And I know that he can get this done, so give him the grant. Whereas people in other minoritized groups don't have access to these things, and for some of these reasons here, and they experience cumulative disadvantage. Here's another picture of it. I just love all the pictures I found of it. This is about economic disadvantage, which exists, right? You can see here, this guy, even though he's white, he's economically disadvantaged. And here we're off to the races at the end of undergrad or whatever. And it's pretty clear who's going to end up at the top. Okay, so what are some conclusions? There's some inequities or inequalities that we can't control. It's kind of beyond our control that society has assigned childcare to women still. We don't have to operate that way in our own homes unless we choose to. But it doesn't mean that we shouldn't change what we can. I'm reminded here of about 25 years ago, a biologist named Nancy Hopkins at MIT went around and measured the lab space of the faculty members in her department and did the data analysis and found that there was a gender gap where women had less space than the men. She went to the dean, who was a guy, and I actually met him, and he's kind of an awesome person. She went to the dean, and the dean fixed it. And so I bring that up because if you're ever in the position like that, you can make sure that people have access to resources based on merit, not on some intrinsic characteristic beyond their control. It may be my last slide or almost my last. Yeah, that was my last slide. So we do have time for questions in case you have any. Thanks very much for listening. I know it was a really different kind of talk than y'all have had so far. Yeah, I see a hand in the back. Yeah, I think I know which one you're talking about. Back. This one?
This is more of like a general question, like when it has like intersectionality, like if you had like, I know this is like accumulated over like things like economic advantage and first and quantify something like first generation students versus like coming from another country or so on and so forth. Like I was wondering if you guys like if you had accounted for those variables, was there any differences seen with, for example, women who are like, Black or like women who come from first generation for students and so on and so forth, but if the no's change to yeses or like.
Yeah, you're asking a really good question that we struggled with when we developed the questionnaire. We actually did not measure any kind of race or ethnicity because it's so different in different countries, right? So the way that race works here in the US is way different than it works in, I'm just picking something up, Brazil, for example. So I think that's a great question and one that we have looked at in the US on US only data. You could see in my tenure study, for example, we controlled for gender and race and ethnicity, and the gender difference went away or wasn't there. I shouldn't say went away. Yeah. But also first generation, we just didn't feel like we had a good way to measure that. So some of this is limited by measurement and the way that different societies work. Thanks for the question. Oh, I don't know whose hand was up first. Okay. Okay.
Thanks for the really interesting talk and really in-depth analysis. It's really great to see. I had a question about the tenure study where you had these box plots. And as we discussed, Hispanic and white and so on, you had a box at the end, other, which actually was lower than white. The one before. That before, yeah. Am I reading this right? So this.
Yeah. I think that was not significant because it's such a small group. But that included people who checked more than one race or ethnicity. Also people who may have indicated that they were something like Middle Eastern or indigenous. So it was just for faculty members, those tend to be very, very small numbers of people. And I suspect that that's why it wasn't statistically significant. Is it, my statistics professor in grad school used to say, but is it socially significant? Answer, yes. So, good question. Was that your whole question or, yeah? Yeah, yeah. Yeah, please.
So going back to your slide 17, unsure what whether these the data are self-reported and what enough means.
They're self-reported in what?
Say,
It is self-reported, yes.
so in that case, what?
Again, that is up to the respondent to define, right? But everybody got the same question. So you're right, it is possible that one group would say, you know, theoretically, if we had an objective measure, one group could come out and say, you know, someone with an accurate measure could come out and say, oh, all the resources were actually equal, but this other group feels that they are shorted. They're not, but they feel that they're shorted. The reason why I don't talk too much about that hypothesis, although I think it probably is in our paper, is because these results are consistent with other research showing that they're, like, for example, there's a lot of research in the US and in the UK about the effect of, well, this is a different chart that I showed, the effect of being a mother on women's academic careers, which is a negative effect. So I think both are true and we don't know.
I never think that I have enough travel money, but
Yeah, funding, who thinks they have enough? But this again is measuring the difference between men and women. But go ahead.
I know many colleagues don't travel much, so they might find that they have fun. So that much they want to deny there's no that.
Yeah. And one thing that, you know, I didn't bring, because I didn't bring that level of detail, and I usually don't in a talk, because like I said, I usually talk to physicists who just want to know what the answer is. Sorry if you're a physicist, or started out as one. Wait, I got distracted by my reference to physicists. Can you say what you said again? Because it was interesting.
See, the lack of gender gap, say what's the law of norms.
Oh,
Simply because.
yeah. Yeah. So this would be in the error measurement in our equation, right? And I didn't bring how large that is, and I didn't show you the statistics on how well the model fits. But yes, there are in any social science model or that's tested, there's unexplained variance that could be due to things that we couldn't measure, for example. Yes, you're absolutely right. Gosh, 3 at once. I saw you in the back first, John.
So when you're looking at these groups, a lot of these groups aren't monoliths. So how do you like account for that? For example, like for Hispanics, there's a wide range of different Hispanics, especially Hispanics that have been here for generations compared to some that as immigrants or sons and daughters. How do you guys?
Well, that's the problem with statistics on people, because to get enough in a group to make the test meaningful, you have to lump a bunch of people together. I've had to do things where it's like white and then people who aren't white, you know, which is not the right way to say it, but anyway. So it's a problem with statistics, and I think that's where qualitative data can be helpful, because you can, when you're interviewing people, start getting at some of the differences between different types of people, like within Hispanics, or there's even, for example, a big difference between people who are African faculty members versus someone who their people were brought here in slavery. So I saw two more hands. Michael?
From the discussion from the previous question, regarding the perceived having enough versus like what the actual resources are. Some of these questions, like enough clerical support, are probably hard to quantify, but for example, funding, like, have you looked at the actual data, like funding, average funding for, question versus
That would be easier probably to do within one country, although I mean, it's just hard to ask people when there's different currency systems and different funding mechanisms, but no, I get it. There are objective measures of some of these things. It's just that that's not what we had. That's not how we designed the questionnaire. So, yes,
You mentioned you used the bond Ferroni
correction. Mhm.
Do you trust it? Because I fundamentally don't like the key assumption that all my hypotheses are independent, therefore I can get this nice value when these are clearly not independent.
I agree with you. They are not independent, and I think that was the best way that we knew at the time. If you have a better way.
I was really hoping you did.
They are not independent. I think it is, I wanted to do it though, because it is very conservative. Ordinarily, we would set our level at 0.05. And so to have it at 0.002, I felt was at least making sure that that it was a real, at least in this data set, effect. Yeah.
And because your significance is so small, did you guys do any power analysis?
Mm-mm.
That's why I'm arbitrary.
Yeah, no, we didn't.
Okay.
Because, yeah, it's wildly arbitrary. No. So I think we're out of town. Oh, good. Y'all can.
For in-room?
Well, let's see, let's start you over. Thank you, Rachel.
Tom, whenever you're ready, you can share your screen.
Yeah, so next talk will be on Zoom by Tom Loredo, and thanks for being here again 3 years later on Zoom, Tom. So I really appreciate it. So, it was wonderful.
Thank you very much for the invitation. I'm not seeing the screen sharing button.
Should be at the bottom.
Yeah, it's not there. Audio, video, chat. Oh, there it is. Just appeared. If I share my desktop and do a full screen presentation, will that work?
Yes, that's what I've been doing on the
Yeah.
podium.
Okay. Okay.
Perfect.
Are you seeing the whole thing?
Yes, all set.
Great. Well, thanks to the organizers for squeezing my talk in and being so welcoming to this topic. And just thanks in general for organizing the second really interesting, kind of astrostatistics oriented meeting at Huntsville. It's really great you guys are doing this. The work I'd like to tell you about is work that I'm doing with a statistician, Robert Wolpert at Duke University. And it's kind of resuscitating work done over a decade ago, started over a decade ago with a Duke PhD student who went off to YouTube, Mary Beth Broadbent, and John Hackala, who you heard from on Friday. And so my title is Salient Feature Discovery in Astrophysical Count and Point Process Data, GRB pulse fitting and beyond. So I'm going to talk about GRBs, and thankfully, John and Eric have provided outstanding introductions to GRBs, so I can assume you guys know what those are, especially the non-astronomers. Hopefully you'll remember from their talks. In his talk, John mentioned Jay Norris as the person originating, or one of the people most involved in studying pulse decompositions of gamma ray bursts. So I just wanted to, I just learned last week that Jay recently passed away, and I just wanted to offer this talk in memoriam of Jay. He's very influential in this field, and he will be missed. Okay, so I'd like to start by reminding you of a very well-known statistics aphorism due to George Box. All models are wrong, but some are useful. The earliest publication of this actually had that featured as a section heading. It was so important to George. But it's worth seeing what he wrote right after the section heading. He says it would be very remarkable if any system existing in the real world could be exactly represented by any simple model. But some models do provide remarkably useful approximations. So that's what he meant by useful, is that the model is an approximation. He elaborated about this in multiple papers and books, and probably most famously in this book by Box and Draper, Empirical Model Building and Response Surfaces. This was in the context of building empirical or phenomenological models, like fitting polynomials or splines, those kinds of things. So this is the context of the most quoted version of the aphorism. The fact that the polynomial is an approximation does not necessarily detract from its usefulness, because all models are approximations. All models are wrong, but some are useful. That's the quote. He added to that, the approximate nature of the model must always be borne in mind. So what I'd like to talk about is addressing the question, how might we quantitatively bear in mind the approximate nature of our models? Or in the language of this workshop, how can we quantify the impacts of systematic error understood as model misspecification? I'd like to discuss this in the context of what I call salient feature models. Salient is an adjective, and it means the most noticeable or important aspect of something, or the most prominent or conspicuous aspect. So a salient feature model aims to capture only the prominent aspects of an observed phenomenon. So it's not expected to match reality with high fidelity. Details that are in the data won't be captured. So in some sense, a salient feature model is a euphemism for a crude but useful model. But these models arise all the time in science. I've been interested in this topic for quite a while. There's just so many talks I hear, especially by theorists, but also by observers, where they'll show some data and then they'll show some kind of predictions from a model that kind of fit the data. But they're suggestive that there's something in the model that's true, but they don't exactly fit all of the data. So these kind of models arise when there's significant uncertainty about the relevant physics or science behind the data. That's very often the case in pioneering studies when there's some new field opening up, a new data set. You won't know much about the physics of the phenomenon. You're just trying to capture like the first order stuff. But it also happens in ongoing studies of very complex phenomena. So gamma ray bursts, Eric mentioned in his talk how long we've studied them, but how complicated they are, still defying a complete understanding. Climate modeling is another example of a field where there's just decades of work. We can make pretty impressive predictions, but they don't fit the data exactly. Cosmology is another example of that, where decades of work, but there are still aspects of the data like the Hubble tension or the sigma 8 tension that we don't quite know how to account for. So we're getting the gist of things, the salient features, but we're not getting everything. So let me give you some concrete examples. So This is fitting the spectral energy distributions, basically the spectra of galaxies with multi-component radiative transfer models. These are plots of spectra as a function of wavelength. So frequency weighted flux density as a function of wavelength. And these are fits from, as mentioned above, in a multi-component model that has a torus around an active nucleus, a black hole accreting at the center of the galaxy, starbursts, a spheroidal component. And what you can see here is that those models, the black is the total of the components, those models do seem to be capturing something significant about what's going on in galaxies, but these points actually all have error bars. So when you see them well away from the line, the model is not fitting. So this model is telling us something. It's captured something that looks impressively on track, but it's not captured everything. So how do we, if we want to, like, for example, quote uncertainties for the parameters in this model, how do we account for the fact that we know that it's not an exact model? This is a case where the statistics is done in a chi-squared fitting with additive Gaussian noise models. Okay. Another example, this is a cosmic demographics example, modeling cosmic populations. Here, modeling the distribution of luminosities of nearby galaxies is seen in the Sloan Digital Sky Survey, or of quasars accreting black holes in distant galaxies. So on this plot, brighter is to the right. On this plot, brighter is to the left because of the strange way astronomers measure brightness in magnitudes. So in these plots, there are some fairly sophisticated non-parametric estimates of the luminosity functions with uncertainties. But to get some theoretical insight into them, they're fit to somewhat simplified but interpretable models. This one's called a Schechter function, this dashed line here. It's a power law with an exponential cutoff. Here, there are also power law models. And I don't want to go into detail in this, but just to say that it's clear these models, I mean, here's the non-parametric fit with an error band. It's clear the model is not fitting everything that's there, but it's capturing something significant. Similarly here, the models, which are the green and red dashed curves, look like they're fitting pretty well, but the error bars are quite small. And in fact, the minimum chi-square values are 2 to 3 times the number of the degrees of freedom. So these models also are not capturing details in the data, but they are capturing some significant part of the trend. Here, the data are individual measurements of things that are distributed like a point process, measured with selection effects and measurement error. And then the example I'll talk about, which you've heard a lot about on Friday and more about today, is gamma ray bursts. These are the light curves, so time series, intensity versus time of a gamma ray burst at 4 different energy ranges of photons. We'll talk more about these types of plots later, but here the data are counts in bins, though some gamma ray bursts also have arrival times for individual photons. So again, photon point process. So what I'd like to talk about is how to at least partially account for model misspecification in this kind of point process data. But I'm going to motivate it by first talking about the notion of discrepancy functions in data measured with additive Gaussian noise. So let's talk about that. Just a few quick slides, a little hand wavy, but just to convey some things that are already well established in the literature. So when astronomers see a too large value of chi-squared, they know there's something up, and there are a couple tricks that we do fairly commonly to handle it. So here's the setting. We have some measurements y. Those are predicted by some function of parameters with additive Gaussian noise epsilon with known standard deviations. And those predictions are values of some function at some known sample points, or sometimes they're functionals of some function. So we're doing curve estimation. That will be important later on, that this is actually a curve, not just a bunch of unrelated values. So we typically fit by optimizing the weighted least squares target function, the so-called chi-squared statistic. It's not really a statistic until theta is optimized, but the residual, the observation minus the prediction divided by the squared error, and then the estimate is the minimizer of that. But it's not too unusual to see a minimum chi-squared value that's much larger than the numbers of degrees of freedom, indicating there's some kind of systematic error. Either the model is just wrong in some way, or maybe we've estimated the noise incorrectly, which you consider to be part of the model. So what should we do in those settings? So there are two common tricks. So one was already mentioned by, I think, Max in his talk. He mentioned that xspec has a systematic command. And this is a quote from the documentation here. It adds, it adds a systematic error term in quadrature. So it basically replaces the sigmas with sigmas. Actually, I should have replaced the variance. It's replacing the variances with the variance plus some number times the variance, beta squared times the variant. And often you will try to use some judgment to set that beta. Another trick that's done doesn't really have a name, and it's too often not even acknowledged, but it's you might call it degree of freedom matching or variance inflation. In that one, once you have your fits, you just inflate all the standard deviations, or inflate by alpha, or inflate the variances by alpha squared, adjusted so that the final minimum chi-squared you get is equal to the number of degrees of freedom. So both approaches in the end use not the original chi-squared, but chi-squared with inflated sigmas in the bottom. So that's just chi-squared over alpha squared, where for xspec, alpha squared is 1 plus the beta that you would use in xspec. So that's just kind of motivated by chi-squared and counting degrees of freedom, but you can motivate it by including an additional discrepancy component in the model equation. So y is the prediction plus the noise error plus a discrepancy term. And if we let that discrepancy be IID with zero mean and a variance of beta squared times the known noise standard deviation, then this is equivalent to a model that just has one kind of composite error term. And that composite error term has an inflated standard deviation. And so that's just a bunch of Gaussians. So it's easy to write down the likelihood function for that. It's just comes out to be chi-squared over alpha squared, the thing that people use to do the fits. But there's also alpha dependence in front from changing the width of the Gaussians from sigma to sigma times alpha for all n data points. So some things worth observing about this likelihood function. If you jointly optimize over the model parameters and this inflation factor, that ends up setting this Q thing, chi-squared over alpha squared, to equal the number of, it ends up setting chi-squared to equal, chi-squared over alpha squared to equal the number of degrees of freedom. The chi-squared with the inflated errors now equals the number of degrees of freedom approximately. Maybe a bit more interesting is that from a Bayesian perspective, rather than just plug in an optimal value of alpha, you'd like to admit that you don't know the scale of the systematic error, so you could marginalize over alpha. You can do that analytically, and it makes the likelihood function not be the exponential of minus chi-squared over 2, but a power law, falling like a power law in chi-squared rather than exponential, so that widens the weights even further than just inflating the sigmas. Now, when you do this, that discrepancy term, those delta factors you've introduced, can potentially absorb or attenuate information in the data that's actually relevant to the model. The fact that all those discrepancies are IID, so each one is considered to be statistically independent, can make the attenuation very non-local. Like, we're doing function fitting. We're not just, fitting a lot of independent measurements to independent quantities. There's an underlying function with continuity. And so we would expect any discrepancy in the model to be correlated with the argument x, like wavelength or time. So this is accounted for in the literature on Gaussian process emulation of computer models by replacing those discrepancy terms with a discrepancy function, something that's forced to be smooth by assigning it a Gaussian process prior. And there's a really sizable literature on this. This is one of the most cited papers. It's a tutorial on it. And I've highlighted here, this framework includes, this is for looking at computational models like climate models, or in astronomy, these techniques are used for cosmological models. Computationally expensive models that can be evaluated on some intelligent grid and then interpolated with a Gaussian process, but then an additional Gaussian process is used to model discrepancy between the simulator itself and any test field data that we might have. So that's the idea. This is known technology for modeling data with additive Gaussian errors. What do you do with Poisson data? Count data or point data? So again, let's return to the gamma ray burst setting. I've shown you again the light curves or time series of gamma ray bursts. These are counts that for strong physical reasons you would model with a Poisson distribution, having to do with the independence of the regions producing the emission. There's also a bit of quantum mechanics that comes in there, but Poisson distributions are strongly motivated for this. So the idea is there's some underlying flux density. It's a function of time and energy, and it's also a function of some parameters, and it will have a background component and a signal component. The background might vary smoothly over the time of a burst. Bursts can be anywhere from a tiny fraction of a second to many minutes long. The background will typically smoothly vary over that time frame, but the signal, as you've seen already in multiple talks, varies violently, typically with the appearance of being comprised of multiple pulses. So we model that with a Poisson intensity function. Did I skip something here? Yeah. Okay. So those are typically modeled with just doing chi-squared fitting, using the chi-squared approximation to the Poisson likelihood function. Maybe some people use the cache quantity that was talked about on Friday, but most of the work I'm familiar with uses chi-squared. You could use the Poisson likelihood. We use Poisson likelihoods in the framework that Mary Beth helped develop with Robert and John. And the way we do that is we consider the signal to be a Levy random field. That's just fancy words for saying a superposition of a random number of kernel shapes describing a parametric family of pulse shapes, each with its own random, in the sense of described by a probability distribution, a random amplitude. There's some interesting stochastic process terminology and technology underlying this, but it's easier to see what it does, how to do this fit in a picture. So there's a space of the amplitude of a pulse, the shape, any parameters, one or more determining the shape of the pulse and the location of the pulse. And we basically say there's a Poisson process that's determining points in that latent space. Each one of those defines a kernel with a particular location, shape, and amplitude. So this red point gives you this kernel. The green point gives you the second one. And then the observed flux is a sum of them. And this particular framing of the problem makes it amenable to some interesting kind of Bayesian calculation technology that I don't want to go into, but it lets you do fits that account for the uncertainties in the locations and shapes of the pulses, but also uncertainty in the number of pulses using reversible jump Markov chain Monte Carlo, or trans-dimensional Markov chain Monte Carlo, a computational technique that lets you adaptively adjust the size of the model in terms of the number of pulses to the data. So I'll show you examples of fits to one particular pulse. It was one that's been well studied, one particular GRB. It's one that's been well studied previously with Fermi gamma ray burst monitor data. And so here you see the data. Again, these are counts. They've been divided by the bin width so that they appear here as photon rate, but they're actually discrete counts, integer counts of photons as a function of time. There's a background. I believe we might have just used flat here. We typically also use like polynomials. And then you can see some fits here. So these are 3 different fits from among many that that our code produces. And there's a total fit. That's a black curve that you could hardly see, but in color you can see the constituent pulses. And so here's a fit where there are 2 pulses that seem plausible, but then there's this strange kind of very narrow one. Here's a fit where what looks visually to be 1 pulse is actually being comprised of 2 pulses. And what we believe goes on here is that we just use computationally convenient pulse shape models. This one's called a Norris kernel. It's not quite an exponential rise and decay. You can see it as a smooth peak, but it's a fairly simple but flexible parametric function. But nobody believes that gamma ray burst pulses look exactly like a Norris kernel. So what happens is that when you fit a pulse, any misfit with your assumed kernel shape gets accounted for in the model by introducing small additional pulses. And so here, where there appear to be 2 pulses in the data, the model actually prefers 4 pulses and says there may be 3. And I think one could possibly make an argument that there's 3, but it seems unlikely visually that there would be 4. So how could we account for this? We'd like to, the way I think of this is that the pulses are salient features. The pulse is meant to describe the gist of what our pulse model, a pulse kernel, the Norris kernel is meant to describe the gist of what a pulse looks like, but not exactly what a pulse looks like. How can we account for discrepancy between the kernel shape and the actual pulses? So we're going to build on the idea from the Gaussian process literature, the Gaussian noise literature, and where they add a Gaussian process discrepancy function. But how could we do that in the case of point process models? An additive discrepancy is, especially a Gaussian one, is not a good way to approach things because the Poisson intensity function has to be positive. So we do this by introducing a multiplicative rather than an additive discrepancy. So to predict the counts in a bin, we compute the expected counts from the salient feature model. That would be a sum of these Norris kernels in a background. And that would give the blue histogram here for some short segment of the data. That would be the predictions from a salient model with a particular number of pulses and a particular set of pulse parameters. And then what we do is we say that the actual Poisson expected number of counts is that lambda multiplied by a discrepancy factor alpha that's drawn from a distribution with positive support and unit mean. And here I show a distribution as an example. And this is a gamma distribution, and I'll say more about that choice in a minute. So when you combine those, one of the reasons for using gamma is that you can analytically marginalize over the distribution for those factors alpha. And when you do that, the net sampling distribution for the data is a negative binomial distribution. So marginalizing over the discrepancy function, now determined by a random draws from a gamma. We can parameterize that by the width of that gamma distribution around around 1, which we call the over-dispersion factor. So we're allowing for this discrepancy factor to increase the uncertainty in its net effect will be to increase the uncertainty in our estimated parameters. And that uncertainty is now a mix of aleatoric, so-called aleatoric uncertainty, borrowing from the machine learning lingo. That is uncertainty that we expect that describes variability under replication, and epistemic uncertainty, that is uncertainty in our model that we think would be the same for a different observation of the same burst, maybe by another instrument at the same time, another detector on the satellite, or in hypothetical repetitions of the experiment. So when you do that when you incorporate that kind of multiplicative discrepancy, here's what the models look like for that GBM data again. And the models tend to make a little more sense now. There's now significant probability that there are only 2 pulses. 3 are still favored. In some cases, yeah.
You're over time, so I'm going to ask you to wrap it up if you can.
Okay. Yep. I'm
Thank you.
basically done. Thanks. Okay. Thanks. So sometimes the third pulse is actually an adjustment to the background, and sometimes it's again seems to be related to model misspecification. So this is my last slide. So as Max mentioned on Friday, negative binomial distributions have long been used for over-dispersed count data. But here we're not saying that there's actual over-dispersion. We're saying the model, the photons are obeying the Poisson distribution. But so the new aspect here is interpretation. The discrepancy factor accounts for epistemic uncertainty. We still expect replication to be Poisson. And then there's a technical thing which is really cool, but I didn't have time today to talk about it, which is the gamma distribution we use is actually constrained in a special way. It respects aggregation consistency to let us kind of self-consistently analyze data of different bin widths. And this lets us actually go to the stochastic process limit, just like was done for Gaussian process discrepancies, and it lets us model point process data like TTE data. So that's work in progress. We're still working out the details of that, but we have the likelihoods. So that's all. This last slide is just to point out that the word salient has another meaning in physical geography, pieces of land that jut out, and I thought that was cute because it kind of looks like the pulses of a gamma ray burst.
All right, that was yeah.
Thanks. Sorry, I went over. I didn't.
That's wonderful, and I'll take the opportunity here to. I think that two things that stood out. One comment is that I think I was discussing with one of the students here precisely what to do when your reduced chi-square is too high, and I think you've just summarized in probably the best way, how to reply to that referee, right? I'm pointing at one of the students who was having we had that discussion. So that's and the other one is that, so where can I read these calculations of yours? Because it seems like you and I were thinking, although for slightly different applications, to the same ideas of I think you call it model misspecification or epistemic errors, and I was so I'd be curious, is this published somewhere?
So there's a little bit of it in Mary Beth's thesis from 11 years ago, which is available at Duke. But her thesis was actually on a computational technique, and this was just one of the examples. So there's not a lot in it there, but I will write it up for the proceedings.
Oh, that would be lovely. So thank you. That answers my question, and I'm sure I'll get in touch with you as well because I really enjoyed. But I don't want to take all the time here. Is there any question? Maybe time for one question for Tom. So yes, would you like to come here? Yes, to the podium so that. Yeah.
Hi, Tom. Yeah, thanks for the great talk. I have one little question, and I don't know how relevant it is in the context of Bayesian modeling, but when you deal with count data, do you make any sparsity assumptions so that as your bin counts also increase, you do not end up in a sparse setup where you have a lot of bin counts that are zero, or do you assume that your total amount of data also increases accordingly?
You mean when decreasing the bin size? I didn't really understand.
No, yeah, kind of like that. So when you, let's say, increase the bin size, do you
Yeah.
also assume that your total number of expected counts goes up accordingly so that you don't end up in a sparse setup where you have a lot of bins with no observations, maybe?
Yeah, so since we're doing everything with Poisson likelihoods, there's no problem with empty bins. An empty bin has information. It means the rate was low in that interval. And so we even can go to the limit. So BATSI, the instrument that John talked about on Friday, produced a small amount of time tagged event data where we actually knew the point on the time axis of the arrival of every individual photon. The newer instrument was still operating Fermi that I mentioned today and that Eric talked about too, actually produces a much more complete data set of that kind of point process data. And that's actually what's most interesting to me. So I'm still working on that generalization of this. But yeah, that can be handled without a problem, at least in principle. I mean, computationally, sometimes it can be more expensive, but
Thanks.
All right, thank you so much, Tom. Let's thank Tom again.
thank you, Max. Thanks,
Yes,
everyone.
thank you very much. Yes. And as we set up actually the other talk, this is an opportunity, just like Tom reminded us that of the something called proceedings, although you might have gotten my emails over the past few months, okay? And this is something that, we have an opportunity, each one of you who wants as an opportunity to publish possibly a short paper, okay? There is a special edition for an astrostatistics journal, okay? That I believe I mentioned again, and maybe I'll send you an email Monday afternoon on your plane ride back, maybe you think about it, okay? So this is really an idea is that there are, words fly away, but, anyway, but if we write them down, they stick as they stick around. So please, each one of you consider, a short contribution as the proceedings.
This is the
And
microphones.
now we will
later on.
this session, okay, with Manushi and the non-parametric estimation. So take it away.
You can go until 37.
All right. Okay. Yeah, thank you. So good afternoon, everyone. My name is Manushi, and I'm a PhD student at Penn State. So I'm studying statistics, and my research is mainly in spatial statistics. So today I'll talk about one of my projects where we try to estimate the spatial covariance function using mixtures of Gaussian kernels. So to give you a little bit of an idea, so like if you have n data points from a spatial process, so the idea is like these data points are correlated with each other, so you can no longer treat them as independent observations, right? So if you look at the figure to your left, so you can see these are some mean winter temperatures in the northeastern region in the US. So in that figure, you can see like there's like the points that are closer to each other, like they have similar values, but as you get further away from a certain point, the correlation sort of decays, like the points would have different values, right? But then like if you see the picture to your right, you can see like that doesn't have a clear pattern. So there's a bit of noise. So like it might help to capture some of the information using predictor variables. And also like one of the other challenges in that data set is like there might be estimates, like multiple estimates from the same location. So like any approach that should be able to sort of account for that as well. Why it is important to estimate the spatial covariance functions is because so that we can get an idea about the underlying spatial process so that we can make spatial predictions, right? And so there are parametric methods as well as non-parametric methods. So like what you see in this figure, like the meta and covariance function, it's one of the most widely used parametric methods. But like when it comes to parametric methods, so like we don't know like what method to apply, right? So if you incorrectly apply the method, in that case, like it'll lead to biased predictions. So that's why it's sort of important to look at non-parametric methods so that we can capture the information in a flexible manner. So in our method, we're using a non-parametric technique based on mixtures of Gaussian kernels. So like, let's say like we have a process y of s, where s denotes a dimensional vector that denotes the locations. So in that case, like we can sort of write this random field in terms of known covariates, as well as a vector of parameters that we had to estimate, and also a process z of s that we assume as a weakly stationary process that has an isotropic covariance function. So what it means to have an isotropic covariance function is that the function only depends on the magnitude of the distance between the two locations and not on the direction, right? So and then also like we can decompose it into an error process. So this error process, it's independent of the z of s, and also like it has a variance of sigma squared e, and the errors at different locations are independent of each other. So we are basically, so we can see like in this one, so like the covariance of y of s, that depends on the covariance of z of s, as well as the variance of the error term, right? Which we call as the nugget effect. And then, so since we assume that the z of s is a weakly stationary process and that it has an isotropic covariance function, we can denote it in terms of the lag distance h, and then we can write the covariance of y in terms of lag distances. So we also assume that this covariance function of z is valid in all dimensions. So what it means for it to be a valid covariance function is that it has positive definiteness. So since it's positive definite, so we can sort of represent this using this mixture representation that's denoted by equation 1. So as we can see, it's sort of an infinite mixture of Gaussian kernels, right? So alphas are the support points. And then, so like the problem sort of reduces to estimating this like alphas and thetas in the infinite mixture as well as the nugget effect, right? And also like we want to make this function invariant to different scales of the data. So if you divide the lag distances and the alphas by a positive constant, so we can sort of achieve that. And let's say like we have, like we set this positive constant to be the maximum lag distance in the data set. So then you can see how that would rescale the lag distances to an interval of from 0 to 1, right? And then, so you can see like, so we have the covariance of y in terms of an infinite mixture of Gaussian kernels plus the nugget effect. And then we try to approximate this using a finite mixture of Gaussian kernels. So now you can see like it depends on alphas as well as thetas. So like the exponential component, it depends on alphas. So how we sort of come up with the alphas is like we consider the effective range. So effective range is like basically the distance beyond which your correlation function becomes negligible. So like we can see like this exponential term, it's characterized by the alphas. So like if you plug in a lower alpha value, that it would decay faster. And if you plug in a high value, then it would decay slower, right? So then how we get the alpha values is by like considering the effective range of the fastest and the slowest decaying components, and we set it to 1 over n, then 0.9. And then once we get the minimum and the maximum alpha values, we interpolate that in a log scale. So why we do that in a log scale is so that we can have more values on the left, like closer to the minimum value, right? So it would give you more faster decaying components. Yeah, so and then the other one, in addition to alphas, like we also have to estimate the thetas. To estimate the thetas, you can either use like weighted least squares method or maximum likelihood estimation. So when it comes to weighted least squares method, so this would be the objective function. So we are basically trying to minimize the deviation of the moment estimator from the covariance function that's characterized by the theta values, right? Yeah, and then we can use non-negative least squares method in here so that we can make the covariance function positive definite. And the other one is maximum likelihood estimation. So here we have to assume that Z of S and epsilon S is Gaussian processes. And then we try to maximize the log likelihood, basically. So we know that when it comes to maximum likelihood estimations, it can be unstable at times, and it can take a lot of computational time. So to sort of deal with that, we consider Fisher scoring method in this case. Yeah, so the thing with Fisher scoring method is like we're using the expected information matrix. So in that case, like we can ensure that it's positive definite, and it becomes a little bit stable. And to sort of address the issue of having multiple estimates at the same location, so what we can basically do is like we can first regress the response variable on some predictors, remove the non-stationary nature of the data, and sort of get the residuals, aggregate the residuals by different locations, and you get the spatial prediction, and you map it back to the prediction that you get from a linear regression model, any model that you fit to regress it. Yeah, so then we conducted some simulation studies to sort of evaluate our method. So we considered a two-dimensional grid where it spans from like 0 to 10 on each axis. And then we consider like a 20 by 20 grid, and we simulate data from a zero mean Gaussian process. So we consider different simulation covariance models in this case, like Matten, exponential, linear Matten, and spherical. And also to check whether our method works across different magnitudes of negative effect, we set the error variance to 0, 1, and 2. And then we try to estimate the covariance function in the simulated data sets using parametric methods as well as non-parametric methods. So we compare our method with another non-parametric method that's in the literature using B-splines methods. So in this table, you can see like the first column. So that's sort of, it gives the prediction error if you use the true covariance matrix to make the predictions. And the blue columns, so those give the predictions using our method. So that are sort of comparable and comparative to the predictions that we make using true covariance matrix too. And also, like, we applied our method on a toy data set, like the mean temperatures in the northeastern region in the US. And we considered different combinations of predictors, like just latitude and longitude, and latitude, longitude, and elevation. And the method seems to work well in both cases and sort of outperform the other non-parametric method as well. So this is another data set. So like we wanted to check whether our method is robust to the presence and absence of outliers too. So like the dark blue bar is for the mixture model using the Fisher scoring method, and that has the lowest root mean squared prediction error in both cases with and without outliers. Yeah, so as like when it comes to future research direction, so like one of the main assumptions that we make in our method is like the covariance function has to be isotropic. So we can also consider the anisotropic covariance functions where it can depend on the direction as well. And also like this method, it works for like cases where we have one response variable. But so in this case, like we're capturing data from like information predictors as well as spatial information. But there can also be cases where we want to capture correlations between different response variables as well. So like that could be one direction that we could go in. And also, so this is just analyzing spatial data. So we can extend this to spatiotemporal settings as well. Yeah, that sort of concludes it. And thank you for being here.
Any questions? Yes, please.
Since you are thinking of applying for spatiotemporal segments with very specific Fourier functions, so if you look at the solar wind data that evolves with radial distance over time, and if you look at the probabilistic properties, they kind of figure out the risk property that is the evolved over distribution time. So it's like you get those data.
Yeah, thank you so much for that. Yeah.
Yeah, right, actually. Now I can connect the dots with your talk. Yes, indeed. Yes, yeah, good. Any more questions for? And if not, let's see what let's thank for the afternoon, and we are supposed to be back at 3:55. Well, let's just do that then. Let's take a short break.
Oh, it's so beautiful. I was not pretty sure that.
There was a little bit of a confusion on one of the speakers who was not here, so. Let me just.
I don't know. So,
They're getting started if you'd like to join, and, but,
Now is the up button to go down. Down is next. Laser pointer. Stay
Okay.
close to the
Well,
podium.
I think, let's just get started, okay? It's slightly,
have until
out of order because
4:10.
one of the
Okay.
speakers is just, not
sure.
here. And, so we
7.
continue with Samuel. We will talk about sequential analysis, okay? So, yeah. Go ahead, Sam.
All right, so we're gonna change gears from like real big astronomy math to very simple like statistics math. So let's go. So a lot of statistics that we get taught, you're given a data set and you assume, cool, this is my data set, this is my sample size. If you want more, you're kind of SOL. Well, what if you wanted to collect data until you could reach a sufficient conclusion? And if you've wondered this, there's a very simple answer on why you're not taught this. Because with a normal hypothesis test, you either reject your hypothesis or fail to reject. And if you fail to reject, you just continue collecting data. So really, there's only one answer you can get, and that's fail to reject. The asterisk on that is you can set an upper collection time to say, but if my sample reaches 50 counts, then I'm good. I can stop and move on with my life and say fail to reject. So this technique is extraordinarily common in like the biomedical industry where they do like vaccine surveillance to say, if I give a group of people this drug for long enough and it looks after a certain amount of time to be super effective, there's ethical concerns to not give it to more people, so they need to be able to stop soon. The opposite of that is also true, where if it looks like it's really dangerous, maybe stop giving it to people. So all of this is prelude for sequential analysis, parentheses, specifically for Poisson counting data, because that's what Dr. Bonamente likes. So a real quick overview is sequential analysis. You just keep collecting a data point or a couple of data points, and then perform your hypothesis test. Your hypothesis test is a little bit different than like traditionally, but we'll get to that. And part of my thesis was arguing that maybe we should use sequential methods more in astronomy, because the broad goal of it is to save money. Today, we're going to talk about two types of sequential testing. WALD's sequential probability ratio test, and that's the same WALD that everybody else loves. And this is just a repeated application of the simple Niemann-Pearson lemma, which compares two simple hypotheses, which are just two models. And this one's really good when you know a lot about the system and you really only care about one or two or maybe three outcomes. And then there is the max SBRT, which is very poorly named, but it was developed more recently, specifically for vaccine surveillance for binomial and Poisson processes. This one is cool because it allows composite hypotheses, but it requires the a priori truncation limit. And I'm going to introduce the very basics of it. You're going to be thinking of a lot of holes and like gotchas for this, and more than likely you are correct. So we can talk about them afterward or at the end of the day. But real quick, there's a lot of astronomical applications if somehow magically you can pull the data off a radar while you're collecting it. So in like my industry, you can do that because they designed it to do that way. I don't know if all radars are that way. So if you can't do that, there's some neat things that we can talk about afterward in which you can use this. But the two things that I really like to focus on are determining the strength of an unknown source to be like, oh, if it's really bright, it falls in this band, or maybe it falls in this band. And you can use like a rapid, rough cut classification algorithm for that. We're not going to talk about that today. Instead, we're going to talk about whether a source exists within background noise, because that one's more fun and you can use fancier tests on it. And there's a potential to save a ton of money to say, well, I'm going to look at the sky until I determine if a source is there or not, and then move on to go look somewhere else and see if a source is on. So, it's everybody's favorite. We've seen the Poisson distribution. Now, imagine, if you will, we were to do a nice little hypothesis test with two Poisson distributions of slightly different rates. So lambda can either be lambda 1, your alternate distribution or hypothesis, or lambda naught, your null hypothesis. We perfectly set these to either of those values, so they are simple hypotheses. Usually you would say, well, it's either lambda naught or it's a lot bigger than lambda naught, or it's different from lambda naught. And in particular, I went into a lot of depth in this because the guy that made this test did not care about the Poisson distribution. So speaking of WALD, we take these two simple hypotheses. You can do this any dimensional that you want, any distribution that you want, as long as you know what your population distributions are. So you can compare a gamma distribution to a Gaussian distribution if you play the games of setting the support up correctly. However, simplest case, let's just look at a Poisson distribution where your parameter, like we saw on the last slide, is either lambda naught or lambda 1. So everybody's favorite, log likelihood ratio, assuming IID measurements. Again, this test is generic. You don't have to assume IID, but it makes the math so much harder if you don't. So in this case, we're going to assume that because that makes life easy. And a fun little derivation for you guys that I can prompt you with the problem later is deriving the thresholds for that. Your threshold is, there's your probability of false alarm in alpha, and your probability of a misdetection or type 2 error in beta. So usually before an experiment, you sit down with your data and you say, I have n data points. Cool, that's fixed. I want my probability of false alarm to be alpha. Perfect, fixed. Null hypothesis, fixed. And then if you want an alternate distribution or you want your probability of misdetection, you have to set your alternate hypothesis as like H1, or in this case, theta 1. And then at the end, you get your probability of misdetection as a function of that. Wald looked at that same math and said, why don't I just flip it and say, if we set alpha, beta, and both of our hypotheses at the beginning, that makes our number of samples variable. Cool. So now let's apply this to some data. I lied. Now let's apply this to some data. So we want to see if a source is present in background noise. Null hypothesis, just background. We've seen a dozen different ways to figure this out. For Wald's test, let's just suppose that we have divine intervention, that we know exactly what the intensity function must be. So for this, we're going to say, it's that nice value. And then we're going to test a series of alternate hypotheses. Because remember, we have to fix our null hypothesis, which was that 0.4 value that you saw earlier. And we also have to fix our alternate hypothesis, lambda 1. Well, fixing it kind of hard, kind of the entire reason that we invented composite testing. So we're going to fix it to a couple of values. And I went the wrong direction. So we're going to fix it to a couple of values. Here's the raw data. Here's your source in black. Here's your background in red. Your background in this particular case is not super important, but you can visually see that after a long enough collection time, there is a source. Excellent. But if you look real close in this region, there's some debate on whether there's a source or not. And I don't know about you, I don't want to turn my radar on for that long because each one of these time steps are like 2 minutes long. So how can we terminate the experiment quickly? Run Wald's SBRT a bunch of times with a bunch of different configurations. So ignoring the circles for now and only looking at the x's tests if there is a source at either, is it 1% stronger, 5%, 10%, or is it double the strength? Well, if you guys remember your significance and power curves, the closer you move your hypotheses to one another, the more data it takes to separate them. And that's that like 1 over square root of n Gaussian approximation. So if they're real close together, we don't break that threshold. But if I move it farther apart, instead of needing 90 plus samples, we might only need 50 or 30. I can't read. Or even just a few to get to that answer. But how do you pick? Is 1% good enough? Is 5%? And so on. Well, that's why we developed composite testing. And composite testing and simple testing both have their own drawbacks. So for this, pretend that you know a lot about the system and you're like, well, my source is going to be 10% stronger, probably. But if you don't know that, there's a lot of other methods that you can use, one of which is the max SBRT. This one comes directly from the biomedical field, and the math in it is a lot more annoying. It uses a closed form critical value that is very neat. It uses this expression, which you'll notice if you recall from like generalized likelihood tests. That's all that is. And the critical value that you derive for it is not nice and generic. You have to use computational approximations, and it runs for a while. But once you get to that, you can then set your null hypothesis as a time-varying function. Very cool. Where have we seen something that's time-varying for our background? Our background in red is time-varying, and we know exactly what it is. So we can set that as our null hypothesis and get a slightly different answer that is generic. We didn't have to pick a 5% stronger threshold. We just had to say, you know, if I collect more than 25 counts, I think I'll call it a day and move on with my life. So this test also works very well and terminates after 12 samples. Something interesting about it is the critical value for it is much more conservative than what Wald's method would predict, or even Wilkes' theorem. There is, and I've had many a debate with people on whether or not Wilkes' theorem applies here, because it doesn't, the closed form critical values don't converge to it. If anyone's curious, love to talk about it. But yeah, I'm out of time, but if you guys have any questions, we can go for it.
Thank you, Samuel. You named the max SPRT after me. That was very thoughtful of you. So where does it get the name?
Well, like the generalized likelihood ratio test, they said, well, what if which, first of all, it is just literally the generalized likelihood ratio test. They just did the critical values differently. But they followed all the steps and then said, what if I took the maximum value in this completely unique and original idea? And then they named it after the SBRT because, like, the problems with the normal XBRT. Ironically enough, I forget which one, but Koldorf and Silva developed this for vaccine surveillance. One of them is an anti-vaxxer. So, irony.
Any real questions for Sim?
Excellent. This is good.
Well, there's always time for questions later on. Yes.
Alpha spending is very significant for the max SBRT, and they play around with it a lot, and they use a lot of different like functions for it, and they use like family-wise error rate type things for sequential tests, and then may or may not mess up on the naming of it. So like the difference between interim analysis and family-wise error rates, there is a difference, but it real minor.
Right. In which case, thank you, Samuel, once again. That's the same, yes. Yeah. And then since actually we had a cancellation, maybe you said Maya, if you would like to speak instead again, so we could do that. And okay.
You do your presenter view.
Should be able to set that up. Are you just
I'm sharing the whole desktop.
okay, let me, so I think if I can extend the desktop.
Oh, I got you.
I think if you open it, I can open it in a window too. That might make it easier.
Yeah, you got it. Does that work?
And then I can share this. Ooh.
Click on Zoom and then share at the bottom. Share maybe just the keynote.
Okay. And then if I drag this all.
It's all
This is just
it's
mirroring.
mirrored, yeah.
Okay. Okay, that's great. That's fine. Let me just start from the beginning. Okay. Let me make this full screen.
Will you lose your notes if you do that?
Probably yes, but that's okay.
Yeah, hold on a second. You're not
Okay.
sharing yet. Share, it's easier to do desktop. And then I make that full screen.
Perfect. That works.
Let's see. Down is next. And then you have until 27.
Okay, great. Yes, can everyone hear me okay on Zoom? All right. I'm just gonna go, and if you can't hear me on Zoom, someone stop me and I'll adjust. But okay, so yeah, hi everyone. My name is Sam Grunblatt. I'm an assistant professor at the University of Alabama in Tuscaloosa, so just a little bit down the road. But today, I wanted to talk to you about trying to improve the robustness of inferred exoplanet population statistics from multiple detection methods. So my background is in observational astronomy. My research focuses on studying the populations of exoplanets. And today I just wanted to sort of give some background on the work that's already been done to understand these planet populations, and also what work needs to be done moving forward to make sure that we can actually infer accurate properties of planet populations by combining all of the sort of current and near future missions that will be characterizing planet populations in a variety of different ways. Okay, so to start out, I just wanted to give everyone an idea of what the planet population or exoplanet population is right now. And so this plot is just quickly going through the detection of planets by year. So here you see everything that's in the solar system. And once we hit 1995, that's when we get the first exoplanet. Then in 2000, we get the first transiting exoplanets. Those show up in yellow. And if we keep going, basically you see we very quickly get to very large numbers. I think right now we're up at, over 4,000. I think we're past 6,000 exoplanets that we now know of. And as you can see, I'll just let this loop through one more time. A lot of these planets were detected using various different techniques. So of course, the solar system planets were detected by seeing that they were moving in the sky. But the other sorts of planets that were detected, first we had the sort of radial velocity population, which is coming up right now. But then after that, you see the sort of proliferation of planet transits. And in order to understand these planet populations, we have to be able to take what we've learned from all of these different detection methods and connect them to one another. So the first sort of work on understanding planet populations, I would say was done via the radial velocity method. So this is just the planet detection method where you're basically looking for the wobble of the star as it's pulled back and forth in its orbit due to the gravitational pull of that planet in orbit around it. And you can actually see the Doppler shift of the spectral lines of the planet being red shifted and blue shifted as the planet goes around in its orbit. And so this detection method generally requires lots and lots of photons to be able to work. And so that means we needed to use very large telescopes that were on the ground. And so the detection methods or detections of radial velocities were really dominated by ground-based facilities that had that took data whenever they could. And so using these sorts of data sets, this was the first sort of data sets where we could start to try and understand planet populations. And because we had all of these, hundreds of potential planet detections around, various different types of stars, we could evaluate our sensitivity to any given planet systematically using some sort of signal injection recovery tests. And so people did this to determine their sensitivity and therefore the overall occurrence of planets in different regimes, different mass ranges and different period ranges around different stars. But as you can see here on the histograms on the right, the observation biases in radial velocity were fairly difficult to correct because planet hosts and non-planet hosts were observed differently. So effectively, looking at this histogram on the top right here, you can see that stars with planets tend to have a lot more observations than stars that did not have planets. And so that makes it harder to sort of compare this as like an apples to apples comparison and get occurrence rates for planets that were statistically robust. And so you can actually see that in some of the earliest papers trying to get planet occurrence rates from radial velocities, where they have all of these caveats. And as you can see, they're a bunch of details that they have to give to basically make their occurrence rates meaningful. And so this resulted in a lot of debate in the community as to what the true occurrence of, even some of the most well-studied planets actually was. But over the last, more recently, like 15 years or so, the transit method has actually become the dominant means of planet detection. And so this is just where you're looking at the light from the star, and then the planet passes in between us and the star, blocking some of that starlight, and we see a dip in the brightness of the star that's very periodic, and then we see it repeat every time the planet goes in front of the star on its orbit. And this method really requires very long duration stares at lots of stars at once, and you need high precision. And so this is basically done mostly by space-based facilities, which is nice because that meant that these surveys are a lot more uniform than the previous radial velocity surveys. And so thanks to these transit surveys, we've been able to detect many, many more planets than we were able to get to with radial velocities. And we have a better understanding of their overall, of how sensitive we were to detecting those planets. So as you can see here, transits are all the yellow points on this plot, and they make up the majority of planet detections that we've made to date. And they've really succeeded at pushing to smaller planets at lower masses, as well as detecting planets at a wide range of orbital periods, from 1 day all the way to sort of 1 year or so. And so thanks to this more systematic study, we've also been able to calculate robust occurrence rates via the transit method. And so this is just showing some of the basically yields from those transit surveys, and then how those yields were then used to determine the underlying planet occurrence in various bins of orbital period and planet radius. And so from studies like this, with a much larger population of planets and a more uniform data set, we can work out things like the occurrence rate of Earth-like planets around sun-like stars. And so that was first done a little over a decade now, where we found that around 6% of planets, sun-like stars, have a planet with an orbital period and a radius that is sort of similar to the Earth. And thanks to the continuation of these surveys, we've been able to now expand that beyond just sort of sun-like stars to all sorts of other stars in our galaxy. And so with the K2 extension to the Kepler mission, 2 examples of occurrence rates for non-sun-like stars that we were able to get are occurrence rates for planets as a function of period and planet radius around white dwarf stars. So there, no planet. This is just an upper limit for planet occurrence, but you get an idea. You can just use the same sort of injection recovery test to characterize that planet population, and we can also do that for red giants. So the sort of future of our sun. White dwarf is also the future of our sun, but maybe even further down the line. But with the red giants, we were actually able to calculate an occurrence rate for the sort of hot Jupiters. And interestingly, when we compared the hot Jupiter occurrence rates of red giants to main sequence stars, we found that there are actually more hot Jupiters around red giants than there are around main sequence stars. And so that can start to tell us about how planetary systems evolve over time, and how planets might migrate from one set of orbits around a main sequence star to a different set of orbits around a post-main sequence or a white dwarf. And this is only sort of continued with TESS. So TESS is sort of the current state-of-the-art NASA mission that's doing this transit science all over the sky. It's basically surveying the entire night sky every 2 years to find planets transiting bright stars. And so that means we can start to study different individual planet populations. And so I just wanted to highlight one particular survey that I carried out with my student Stephanie Yoshida a couple of years ago, where we targeted stars that are part of the galactic halo, and specifically looked to see if we could detect planets around these sort of very unique stars with unique kinematics. And what we found is that although we were sensitive to hot Jupiters, we couldn't actually detect any planets around the sample that we looked at. We looked at around 1,100 stars. But from these results, because we had done this injection recovery, we were able to predict that around 10 times as many halo stars have to be searched with this sort of similar test precision in order to distinguish the occurrence rate of planets around these stars from the occurrence rate of planets around the stars in the Kepler survey, for example. But this is about to get a lot more intense, or the number of systems where we can detect these planets is scheduled to basically increase by orders of magnitude in less than a year. So the Nancy Grace Roman Space Telescope, which will be launching or supposed to launch in October 2026, is going to be probing the center of our galaxy to look for planet populations there and characterize how planet populations in the galactic bulge might be different from planets closer to us that we discovered with Kepler. And so one particular survey that the Roman Space Telescope will be carrying out is its Galactic Bulge Time Domain Survey. This is a survey of around 2 square degrees of the sky with a 15-minute cadence, where they'll be covering that 15-minute cadence for around 72 days per season for 6 seasons over 5 years. And so in this 2-degree area of sky, it's expected that we'll observe tens of millions of stars and can detect over 50,000 new planet detections. And these planets will be a completely different population than what we've been looking at with Kepler and TESS, because they'll be so much further away, either in the galactic bulge or in that general direction, that really changes what population of planets we're looking at and what we can infer about the planet population across our galaxy. And so just to break this down a little bit more, from Roman, the Galactic Bulge Time Domain Survey, one component of it is the transit survey, which will work just like the other transit surveys from Kepler and K2. We'll just get light curves for tens of millions of stars, and hopefully we'll be able to detect some transits around them. Based on some statistical arguments, we expect that we should detect between 50 to 200,000 planets via the transit survey. And these planets will be around all different types of stars. They'll be all different types of sizes, and they'll enable these population level analysis of all of these different subsets of stars as well. So thinking about the white dwarfs or the red giants that I already showed before, but also other types of stars, or even things like exomoons as well, potentially even free-floating planets as well, although those are not part of the transit survey. But generally, the planet yield from the transit survey will be closely correlated with the stellar composition. And so by finding out how many planets we actually find in the survey, that'll actually tell us something about the composition of stars and planet populations across our galaxy, instead of just in our sort of solar neighborhood. And so to show this a little bit more, this is just a plot of the planet yield that's expected for different size planets around different types of stars in different components of the galaxy. And so this is all shown as a function of distance in kiloparsecs. And so what you can see is that the vast majority of planets that we're going to detect are sort of at this 4 to 8 kiloparsec distance. That's centered right on the galactic bulge. So we think most of the planets that we find from the survey are going to be part of the galactic bulge, a sort of separate population that we haven't really sampled with exoplanet statistics just yet. But in addition, a big part of the Roman survey will be microlensing detections as well. And so the way microlensing detections work is that essentially a star will pass. Let's see if I can get one of these videos to work. Oh, I'll get both at the same time. So one star will pass in front of another, and basically the gravitational potential of the lensed star will bend the light from that background source star, and the way that that light is bent will basically tell us what's orbiting around that lens star. So if you see basically a little additional blip, see if I can get that to go one more time. Little additional blip. So if you look at this light versus time here, you can see the overall event, which takes sort of weeks to months of that gravitational microlensing. But then you also get this little extra blip if there's a planet there. So there's that little blip, and that you can use. That planet blip is a much shorter duration event. So you really need this balance between the month-long cadence of the seasons, but also the short duration, like hour-long cadence to detect these planet events. And so the microlensing survey actually uses the same exact data as the transit surveys. It's just light curves, but it's a very different sort of system property that it's going to constrain. Let's see. I think I started running these. There we go. So the microlensing survey is nice because it probes a region in space that we weren't sensitive to before. It's getting down to sort of lower mass planets that are in separations that are comparable to the Earth, and it can almost detect an Earth-like planet in an Earth-like orbit around a sun-like star. So if we combine these transit and microlensing surveys, we can really understand a much wider range of the planet population than we've been able to get to before. In particular, we can really start to detect planets that are actual solar system analogs. So we have that sort of sensitivity to detect these planets. But it's important to note that via microlensing, we get a planet to star mass ratio, whereas via transit, we get a planet to star radius ratio. And so to put either our microlensing results or our transit results on this plot, there's a fair amount of sort of massaging and some like manipulation of the population so that we can actually compare these two populations. And so thinking about all of the details that go into making those sorts of like combining these two very distinct data sets is really important for getting those occurrence rates correct. And in addition, even free-floating planets should be found via the Roman microlensing survey. So that's giving us a whole other sort of lever arm to understand the planetary populations. But as you can see here on this plot, the sort of information that you get is the number of detections versus an event timescale. So even just converting that into planet mass is difficult. And so you can imagine then converting the planet masses into something that we can understand the larger planet population context is going to be very confusing. And so we really need to be clever and thoughtful about how we're combining all of these population statistics. So in general, that's more or less what I have. Over the last 30 years, exoplanets have gone from non-existent to Nobel Prize worthy. Earlier demographic studies revealed important details of planet occurrence, but now we have this opportunity to combine lots of different exoplanet demographic surveys. And so we want to be clever about how we're actually combining them, making sure that we're considering the observational biases that are different for each one of these different populations, each one of these different methods, and combine that all together so that we can optimally constrain exoplanet occurrence from all of these new current and future missions. Thanks very much, and I'll take your questions now.
Yes, please. After the transit survey of planets, for the thing that we that the group of those stars that have like mass compared to the arm, that block like this kind of frame.
See if I can get it. One more.
Next time.
There we go. So I think that is probably a real effect. So one of the first things that we that have come out of the Kepler survey that I didn't show today is the majority of planets that we have found, the majority of exoplanets that we have found have a mass range between around 1 and 100 Earth masses. And actually, the most common radius is around like 2 to 4 Earth radii. And so it turns out that there's just a lot more planets in that kind of range. However, when we go from the planet transit results into converting them into planet masses, in order to do that, I would say 90% of these planets probably don't have independent mass measurements, which means that they probably use some sort of mass radius relation. And that might have biased all of those, like 90% of the detections there. And that's why they're showing up as this sort of clump. But I would say there's some other features, like there might be a bit of a like a dip in the amount of planets that we're seeing right there. And I think that's actually something that's real. We actually see that there's sort of a double peak to the small planet distribution, one corresponding to rocky planets and one corresponding to gaseous planets. And around 2 Earth radii, we actually don't see very many planets at all. And I think that's showing up as this little gap in the distribution there.
I was curious, the little dip that happens whenever there is a planet, so does it happen at what point in the light curve? I mean, that movie was really.
I keep going the wrong way.
Me not being an expert at all. So.
You're saying the microlensing light curve?
Right, right.
Yeah. So you can see the sort of overall effect. This is like as the star basically
Right.
crosses in front of the source star. But you also have
Oh, I
some
see.
planet here. And so basically the idea is that as the gravitational well of the lens star is what's causing the general lensing. And so when you add the planet on top of that, then its gravitational well is adding that extra sort of quicker effect.
Detectability is also a function at what point in the orbital phase the planet is, right? Because it can, maybe it's a
Yes.
signal to noise issue. Or,
So
yeah.
when you calculate occurrence rates for microlensing results, you're calculating them in they're not actually in physical parameters. You're constraining the planet to star mass ratio, but then you're also constraining the projected semi-major axis of the planet.
I see.
Because basically the strength of the signal is related to those two things. And so then deconvolving that into actual like physical coordinates, like the true semi-major axis or the true planet, is not trivial.
Is there a lower limit to the planet mass you expect to be able to find via these microlensing methods? I know that the plot mostly bottomed out around Earth size.
So I've heard that we should be able to detect things down to a moon mass. That seems optimistic to me, but I don't think it's possible. But it would require sort of like the best case scenario. And I think thinking that the minimum would be around an Earth mass is probably reasonable. In the most recent like occurrence yield statistics that I've heard, they said that they should detect a few like Earth mass planets on Earth-like orbits.
If there are no more questions, then, thank you. Thank you. And this is just a reminder then that, well, 3 days have come and gone, right? And so there's tomorrow left for this workshop, and we still have a few, I think, very interesting talks in the morning. And this was the main idea that, why don't we reserve a Monday for a panel discussion? So still a few talks, and then the idea is that of having a panel discussion, which is, I just really jotted down a few thoughts, but maybe if you have other ideas, then we can add those as well. No, he's talking to me tomorrow.
Oh, all right. Wonderful.
It is trying to be late, and let's not as originally scheduled. So I guess I will see you all tomorrow morning at 9 o'clock. Okay.